either you gave them to me or I printed them out from your submission without a name on them. So when you submit papers in the future, at least put your number on them. I think this is yours. So the number you see is out of 30. I'm sure this is yours. So you got so score out of 10 for each answer you made. I think this one is yours. You're Josh, right? Now, if you have any complaints at all, or anything you just don't understand, you can't read my writing, which actually happens sometimes. It's not true of all human beings that they can read my handwriting. So, if you have a question about that, or if you just think I was unfair, I'll always listen to a reasonable complaint. The only thing I ask is that you please try to at least try to figure out what I thought was wrong with you. Because if you didn't get a perfect score on anything, sometimes even if you got a very good score, you'll see there's a lot of crap written in the margin. But certainly if you do get a perfect score, there's crap written in the margin, explaining why. I was thinking of putting up some of this. It's really interesting. You have to use two different keys. Go to the top one and the bottom. I wanted to talk about, I talked a lot about the theory of general relativity. And so I just wanted to talk about the philosophical ideas that went with it. I wanted to put some of those quotes up on the screen. The pictures won't do you any good, I guess, because you've seen them already, but we can point to them. Maybe I just turn the computer off. See, the other classrooms I teach in, nobody gives a damn about how these things are. Cables and stuff. If there wasn't a piano here, this wouldn't be usable. So I quickly keep the lid down. It'll almost be like having a mouse pad. I started using a PC, I think it was the year 1986 or something. If you told me I'd still be pressing Control, Alt, Delete 30 years later. I was mistaken about a lot of things. The two minimal things I would have said was, like 2016, there'll be flying cars and we won't be pressing Control, Alt, Delete anymore. So if anybody have any questions about the assignment, I'll put up the next one this week. All right. I meant to do that before I came in here. Because I did actually may make up another set of questions like these for during Slack week. I actually have a Mac myself, but that said Windows 7. What Windows are they on now?
10.
Okay. Well, that explains a lot. So we're just way behind, right? Does anybody have any questions about anything before I start? Let's do anything? What do those say, computer? I hope these are right. The right notes. No question? Now, if you've been following along in the notes, you know, sorry, it's primitive non-wireless stuff. Kind of gets to you. Is anything there say slideshow or anything? Oh, there it is. Okay. So we'll, why isn't this? What is this thing doing? There we go. So we talked last week about the whole mock question. I wanted to talk about the implications of the theory, and I don't remember how far I got with this last time. You know, I told you about Mach's principle, and you read about it, and this basic idea he had that there's something wrong with the theory that says too much, that tries to say that for absolutely any circumstances what would be true. And so that's essentially, as Mach thought, that's equivalent to an interpretation of the laws of nature that says they just hold absolutely. And Mach's view of laws of nature was very peculiar because he thought, you know, you can't take the Newton's laws and say what would happen in a completely different universe, for example, in which there was just a rotating Earth and no fixed stars. Because, of course, he knew that the laws do tell you exactly what to think in those circumstances. But he just thought that was wrong. You shouldn't think of the laws of nature as being abstract, formal truths like that, and just follow their logical implication. Because the real basis of the laws is the dependency they find among the phenomena. So the dependency that he found among the phenomena was the way in which the motions you observe relative to the fixed stars depends on the local forces that are acting on those bodies that have those motions. So the acceleration of any planet relative to the fixed stars depends on the influences exerted by the other masses. He says, now that's a fact about nature. If you want laws of nature that express facts, that's what Newton's second law really says. But if you take it as an abstract law and say F equals ma in some, universally, no matter what else, no matter what the configuration of the universe is, well, then you're just claiming to know too much. It's all right to say that for convenience, but you should really know the foundation of the laws of motion is a kind of an inductive generalization. So Einstein part of his motivation for the general theory of relativity was to make this into an absolute principle. We shouldn't have a physical theory that tells you what would happen if there was nothing but a rotating Earth. Our physical theory should only tell you how local inertial effects relate to the global distribution of masses. And that's, I explained last week, or 2 weeks ago rather, how that got us into the situation of, how did that get us into the situation where we're thinking of gravity as equivalent to space-time curvature? So if you have any questions about that from 2 weeks ago, this is a good time to ask them. No? Everyone followed that? So these are some quotes that sort of express Einstein's philosophical view of how the Newtonian theory works. Well, there's something wrong with the theory, and also wrong with special relativity, just because it tells you something that depends on coordinate systems. Right? So the special theory of relativity, what he was trying to do was to get rid of a special coordinate system that belongs to the ether. Right? It's at rest with respect to the ether, because he said this plays no role in our understanding of electrodynamics. However, there's this infinite number of special coordinate systems in which the speed of light is the same in every direction. Those are inertial frames. Right? Just as in Newtonian physics, there's a special group of infinitely many coordinate systems, all easily related to one another by the Galilean transformation, in which forces are always proportional to mass times acceleration. But what about all the other possible frames? Right? What about all the other frames in which, in which that Newtonian condition isn't true? Or what about all the other frames in which the speed of light is not the same in every direction? Why is it that a uniformly moving frame of reference is privileged, whereas a rotating frame of reference is supposed to be the wrong frame of reference in which to do physics? And Einstein had an idea that these theories were giving a special role to coordinate systems that was wrong. That somehow our coordinate systems are artificial and they shouldn't really play any role. Now we talked about the equivalence principle. Well, I'll come back to that in a moment. Let's just think about this is the basis of his epistemological criticism of the older theories, including his own, and his epistemological argument for general relativity. This is supposed to apply to any theory in general. You see what this is why I'm talking about it, because it's such an important part of his general philosophy that was supposed to justify this particular theory. And this had a huge effect on philosophy of science after Einstein, and also on other younger physicists who were at the same time working on quantum theory, or shortly thereafter. So we'll get to those. We'll sort of segue from Einstein's philosophy into early quantum mechanics. Because, if you have a causal explanation, like you want to causally explain why is the rotating planet bulging out at the equator, but the other one isn't? Well, Newton had a very straightforward view of this that very few people in Einstein's time, including Einstein, appreciated. Newton's view was very simple. Well, by definition, the one that has the centrifugal forces is the one that's rotating. That's how the theory works. That's just what it means to be a Newtonian world. And Mach also thought that. Just as Mach thought, well, it's a leap beyond the evidence to say if you got rid of the fixed stars, the same rotation would produce the same centrifugal effects that it does when it's rotating relative to the stars. But Einstein was making a more absolute epistemological claim, that you have to have a causal explanation, and if the cause is something like a mathematical artifice, like a kind of coordinate system, well then that's wrong, right? He said, well, this is, in Newtonian physics, it's a factitious cause, so it's something that was invented, basically, an artificial mathematical distinction. The cause of an observable effect must be something observable, and there has to be a closed causal chain. This is two kinds of argument here, right? One is, well, if there's something happening to the Earth when it rotates, you see a centrifugal force, right? You can't blame that on something unobservable, like the structure of space-time. You have to blame it on something else you see. So it must be the distant masses that are involved somehow. And the other thing is, well, if you did have something like the structure of space-time involved in a causal interaction, well then it wouldn't really be a causal interaction unless it was a real interaction. That's what he means by a closed causal chain. And so you say, well, if you give an explanation that sounds like this, the reason why you're suffering these inertial effects is because you're deviating from the inertial path in space-time. Or you're on a rotating body, so the body as a whole consists of particles, all of whose trajectories are non-inertial. They're all accelerating relative to inertial trajectories. Now that sounds like, at least this is what Einstein thought, and many other people thought, and still people do think like this, because people still argue about these things. That means that space-time, the geometry of space-time, is doing something to bodies. Right? If you think, well, if I throw a baseball in the air, and it's following an inertial track, that means that it's kind of like following a railroad track, right? There's something about this geometry that's holding it in that path. Of course, the geometry isn't really doing that. It's not really going in an inertial path. It's simultaneously executing its inertial motion and doing whatever the force is telling it to do, so you get a parabola. But still, it sounds like when you put it that way, that the space-time is doing something. So why does that make sense? Was Einstein's question. How can that possibly make sense? The space-time is doing something to the material contents of space-time. But the space-time itself is completely unaffected by the material contents themselves. Do you see what I mean? Like, so Newton says, well, space-time is always the same, right? Space is always the same from moment to moment, and space-time is kind of, and special relativity says the same thing, right? There's a space-time structure that's just uniform, it's the same everywhere. If you draw a light cone anywhere, it looks exactly like a light cone anywhere else. And it remains that way from the beginning to the end of time. And there are all these material things in the universe, but they don't affect it. But it affects them, apparently, because the causal structure, the light cone structure, is a part of space-time that does something to you. It keeps you from, keeps you from going too fast, for example. So that really bothered Einstein. He thought that space-time, as usually understood, didn't fit into a coherent causal picture. Now these two, I mean, I don't know how much you'll want to get into this, or, these are really kind of jumbled motives. They don't really make sense together, even if you like them individually. They're not really coherent. But I'll come back to that. But the main point that he tried to draw is this point about general covariance. In other words, we talked about this a bit. I think I showed you the Lorentz transformations, right? That's what in physics you would call that relativistic invariance. That means you can change your coordinate system however you like, and as long as you leave the speed of light the same. So all the coordinate systems in which the speed of light is the same, those are the acceptable frames of reference, just as in Newton's case, right? All the coordinate systems in which the forces of masses and accelerations are the same are equal. But any other frame of reference is not equal. If you take some function of the coordinates in Newtonian physics or special relativity that takes you from this rest frame to another one that's just moving faster uniformly, that's fine. If you take one that, if you change the coordinates in such a way that this frame of reference is now rotating, then that's not acceptable because now the forces will be different. They'll be wrong from a Newtonian point of view, or the speed of light will be wrong from a special relativistic point of view. But Einstein, for all these reasons, he says that's an artificial distinction, therefore we want a generally covariant theory. Not Galilean Newtonian relativity, not special relativity, his own theory, but general relativity. Any frame of reference at all is supposed to be acceptable. Because coordinate systems are sort of meaningless. So we went through these arguments about the equivalence principle and why that was so important. I'll actually keep this one. So the whole, if you remember from 2 weeks ago, the whole point about the argument about the equivalence principle was that this Newtonian and special relativistic absolute distinction between a uniformly moving frame of reference and an accelerating one breaks down, because you can't tell the difference between a gravitationally accelerating system and a rest frame, or a Newtonian or a special relativistic inertial frame, because everything happens in the same way if you're falling in a gravitational field or if you're moving uniformly. So what does that mean? Well, I got my slides on the board. We talked about all these, well, not in such detail. I did talk about most of this. All I want to talk about from these slides is just these philosophical remarks. And so to get back to this point, what did the theory do? What did the theory that Einstein came up with actually do to realize all these philosophical aims? And we saw one thing it does, is it breaks down the distinction between inertial frames and falling frames. But of course it doesn't break down the distinction between inertial motion and any other kind of motion. It just radically changes it. It just says, well, the inertial motions should now be thought of as equivalent to the freely falling gravitational motion. But of course, if you were falling in a magnetic field because you were trapped in a metal box and had metal clothing on and were being pulled toward a big magnetic source, right, you would be able to do experiments that told you that that's what was happening. Whereas the experiments you do, if there's nothing but a gravitational field, right, those will be incapable of telling you the difference, at least on a small scale, between whether you're falling or moving uniformly. So how far does the theory go? Let me go back to this other slide that I was going to talk about. I assume you guys look at these slides. So if you have any questions, if you want me to stop and explain any of them, if you looked at them online, because I think they're there, you should let me know. Because I'm just gonna, because I'm mostly focusing on these philosophical questions today, and just pointing to whatever I like from these slides to illustrate them, and I'll just be jumping all over the place. So if there's anything in the slides you wanted me to explain, you can stop me. I think much of what's on the slides I kind of hastily drew on the board 2 weeks ago. So this slide kind of illustrates the question, what's the difference really between an inertial frame in special relativity and an inertial frame in general relativity? Well, we saw the basic motivation for adopting a curved space-time geometry was that you have these paths that you have every right to regard as the geodesics of space-time, but they behave like the straight lines of a non-Euclidean geometry, right? They have this sort of deviant behavior, right? Because two geodesics of a flat space-time, if they're parallel, they'll always stay parallel. If they're not parallel, then their divergence will always stay the same. They'll always be moving uniformly relative to one another. So if I'm in an inertial frame and you're in an inertial frame, then my frame looks inertial to you and yours looks inertial to me. We could argue about who's really at rest, but we are too sophisticated for that because we have known all about this relativity principle since the time of Galileo and Newton, so we're not going to get into that. Or if we did get in an argument because of the ether, well, Einstein has gotten rid of that, so we're not worried about a special ether frame, right? But if you do an experiment according to special relativity, and the speed of light is the same in every direction for you, and I do a similar experiment and I get the same result, then your frame of reference is going to look inertial in my frame of reference. Because it's going to look like you're moving uniformly in a straight line with respect to me, and vice versa. And that means that I can take my inertial frame and make it, a coordinate system that covers the whole universe. And every other inertial frame will be captured, so to speak, by that inertial frame, because every other inertial frame will look inertial in that sort of global inertial frame. Whereas if we're falling in gravitational fields, well then your inertial frame will look inertial to you, but not to me, because it'll look to me like you're accelerating away from me or toward me. Even though locally we'll be feeling we don't accelerate. So this kind of leads you to a clue. Well, the theory isn't really saying, well, any coordinate system is as good as any other. So what does it mean to say that there isn't a special class of inertial frames anymore? Does it mean that a rotating frame is as good as an inertial frame? It doesn't really mean that. Because if you're in an inertial frame, if you're in a rotating frame, there still will be centrifugal forces that wouldn't exist if you were in a non-rotating frame. And there's nothing that Einstein's theory can do about that. But what it does say is, what it means to say that the special class of inertial systems is now undermined, it means it has more to do with, not so much with making motion more relative, but making space-time more local. It has to do with local and global consideration. So what it really means is, not that every coordinate system is as good as any other, but that there really aren't global coordinate systems anymore. Because if I'm in a freely falling frame, I'm an inertial observer, I try to extend my coordinate system to a large, to cover the whole universe, I can't do that anymore. Because in my inertial system, it'll look like your motion is accelerating and your light cone is distorted. And vice versa. But that's kind of an important fact. It means it's part of what makes it a non-Euclidean geometry. Right? That you can't extend your inertial frame over large areas of space-time. So if you were to sort of take a point on an inertial trajectory and say, what does the space-time look like at that point? You look at it in a magnifying glass. Well, yeah, if you look at the small area, right, it looks like special relativity is true. And that's a feature of space-time according to general relativity. It's just true everywhere you go. And in a sense, that's kind of goes against Einstein's initial philosophical idea that space-time shouldn't have any sort of objective features. It should all depend on the distribution of mass, because it's still true, according to his theory, wherever you go, over a small region, it looks like special relativity is true. But the larger of a region you take, I mean, it's like that thing with putting a sticker on an apple, right? The smaller the region is, the easier it is, or the smaller the sticker is, the easier it is to make it fit nice and flat on the side of an apple. If you make it too big, then it'll be wrinkled when you try to stick it down. That's really kind of more like the role that coordinate systems play. Right? So if you think, well, it's kind of like being on a non-Euclidean surface, because I can have a kind of flat plane, and I can say, the privileged direction of up is perpendicular to my plane. But if you live on a different part of the Earth, then you can say, well, no, the perpendicular to my plane is the privileged direction is straight up. And until we figure out that we just live on a curved surface, and nobody's local plane can be extended to cover a large area of the surface, then we'll just be in a stupid argument about what's the true direction of up. But the ancient Greeks resolved that argument because they realized the Earth is a non-Euclidean surface. It's not the Euclidean plane. And so it's only over a small area that you can consider that the planet is like a plane. But you can't extend your plane to a plane that sort of fits other people's planes into it. And that's the same thing with the structure of inertial frames in general relativity. But I want you to pay, there's a really important point about this. It has to do with coordinate systems and what they mean metaphysically. Because you could say, I'm sure it makes sense to you, at least I hope it makes sense to you. And it seems like it makes sense to me anyway. When Einstein says, nature doesn't really have coordinate systems. I mean, if I decide to put the origin here and these are my axes, that's completely arbitrary, right? My coordinate systems don't define reality. They're just a convenience for me, right? And space doesn't have coordinates built into it, right? That's why people set them up. When I was a kid, there was this show on TV called Star Trek. Just Star Trek. And they were always talking about coordinates. And that always sounded really technical and scientific to me. And then, when I learned a little bit of math years later, I thought about that. And, well, I guess, if you're on the Earth, you can always talk about coordinates, because you can have a GPS that has got, a conventionally assigned longitude and latitude for everywhere you are. Right? Your phone probably has one. So you can verify that this is the case, and you kind of know how that's done, right? But if you're out in space, and somebody says, beam me to these coordinates, like, what's that? I mean, maybe they do have some system, but the point is, there aren't coordinates out in space. And you could say, well, maybe if this particular spaceship has this coordinate system kind of worked out, and if they send people down to a planet the people down on the planet are somehow fixed to this coordinate system, that maybe they could set it up that way. Of course, but if another ship came by, there's no reason why any two of them would agree on any sort of coordinate system in advance. It just wouldn't make any sense. It would make less sense, right, that if an alien civilization came to the Earth and you tried to explain to them where you are by just giving them your latitude and longitude, there'd be no reason to think that they had a similar kind of coordinatization of the Earth. On the other hand, it's a really important fact about the Earth, right? That you can't coordinatize it in this way. Do you see what I mean? Yes, it's true, coordinates are arbitrary, and anyone can write any coordinate system they want, and they're a mathematical artifice, and Einstein's right to think, you know, well, nature doesn't care about our puny coordinate system. I mean, why are there so many of them anyway? I always thought that was a bizarre remark. I still don't get that. But it's also true that, you know, it's a fact about a surface that you can put a flat coordinate system on. It's also a fact about a flat space-time that there's so many inertial frames. Why are there so many? Because it's flat. That means there's really only one, or there's none, or there's infinitely many. It really doesn't matter. The point is, if there's one way of coordinatizing the whole space-time, then there's infinitely many more, because you can. Well, just think about it as the blackboard, right? If there's one coordinate system you can sort of put on this blackboard to cover the whole thing, right? Well, anybody who wants to can sort of slightly turn the axes. Oh, look, here's another one. It's just as good as the one you started with. Oh wait, let's move the origin over here. Or let's move it over here and turn the coordinate system. Right? Yeah, we can do all these things, but the point is it's a fact about the flatness of the blackboard that you can cover it with a coordinate system. And it's a fact about the sphere that you can't. Of course, you can cover with a polar coordinate system, like the longitude and latitude system, but even then you can't really cover the whole thing at once. This is an interesting fact about